Let's simulate a little more realistic cache. We begin with the simulation of direct mapped cache. Here's our configuration. It's a 4-bit machine, so memory address space is 4-bit. Cache is small, so it can hold only 8 bytes. The cache line size is 2 bytes, so there are total 4 sets. Based on this configuration, the memory address is decomposed into 1-bit block offset, as we have only 2 bytes per line, 2-bit set index, as we have 4 cache sets. The rest 1 bit is automatically tag bit. Now we assume that CPU requests memory addresses of 0 followed by 1, 7, 8, 0 in order. The first memory address CPU request is 0, which is the 0000 in 4-bit binary memory address. The first step is to use a set index to locate a set. It's 00, so it's the first set, number 0. Now we move on to step number 2 and compare tag bit and check valid bit. Because it's the first cache access, the cache is empty, and not only the first set does not have a tag bit, but also the valid bit is 0. Therefore, it's a cache miss, and it's a cold or compulsory miss, as this is the very first access of this cache line. Because it's a cache miss, the hardware accesses low-level memory hierarchy and load a cache line that has a memory address 0 into this set number 0. Once it's loaded, the hardware does a step number 3, which is to use a block offset to locate the target memory address. The block offset is 0, so the hardware returns the first byte out of 2 bytes in the cache line. Now mission completed. The second memory address CPU request is 1, which is a 0001 in 4-bit binary memory address. We do the exact same thing as the previous memory request, but at step number 2, the set number 0 has a matching tag and valid bit is 1, meaning it is cache hit. Now we perform step number 3. The block offset is 1, meaning the second byte out of 2 bytes that this cache line has. The data or instruction at this address is returned to CPU. It was a cache hit thanks to the locality where 2 consecutive memory addresses were accessed back to back, and the cache line has 2 bytes. Next memory address is 7, and it's 0111 in 4-bit binary memory address. The target set is 11, which is set number 3, which is the last set. It's empty, so tag comparison and valid bit check should both be false, so it's a cache miss. Again, this is a cold or compulsory miss. The hardware load a line that has memory address 7 into the cache from the low level and perform the step number 3 and return data or instruction at that memory address 7. By the way, when a new cache line is loaded, the tag bit is updated as well with the tag bit from memory address, which is 1 in this case. Next memory address is 8, and the set index is 00, which is the first set. Now we compare tag bits and check valid bit. The valid bit is 1, but tag bit does not match. 0 in the cache and 1 in the memory address. Therefore, it's a cache miss, and this is a cold miss, as this is the first time to access this cache line. Now, the hardware evicts the existing line and load a new cache line that has a memory address 8 and 9. Once it is loaded, the hardware uses a block offset, which is 0, and return the first byte out of 2 bytes in this cache line, which is memory address 8. Now, the last memory address CPU request is 0, which is the requested before. The target set is 00, which is the first set. The valid bit is 1, but tag bit does not match. So it's a cache miss, and this time it is a conflict miss because this cache line was loaded before but evicted later. The hardware has to load this cache line from low level once again. In this direct mapped cache simulation, there was only one hit out of 5 accesses, so the cache hit rate is only 0.2 or 20%. Now, let's simulate the exact same memory address request with the two-way set associative cache. Everything is the same except now the cache has 2 sets because each set has 2 cache lines. Because of that, the memory address has only 1 bit set index and 2 bit tag bits. The first memory address is 0 and set index is 0, which is the first set. It's empty, so it's a cold or compulsory miss. The hardware loads a cache line from low level and put it in one of 2 cache lines in this set. Let's assume that hardware puts it in the first cache line. Once it's loaded, it performs, of course, step number 3. The second memory address is 1, and the hardware performs the exact same thing, and it's a cache hit. Next, the memory address is 7, and it results a miss, and a new cache line is loaded into the first cache line of set number 1. The exact same process happens as the memory address 0 that we did earlier. It was a cold miss. Next memory address is 8, and it results a cold miss, and a new cache line is loaded to set number 0. This time, no cache line is evicted because the set has an available place to put this new cache line. This makes the difference from the direct mapped cache. It was a cold miss as it was the very first access to this cache line. The last memory address is 0, and it results a hit as the cache still has the cache line that holds this memory address. Note that it was conflict miss in our previous direct mapped cache simulation. Now, the cache hit rate is 2 out of 5, which is 0.4 or 40%, better than direct mapped cache. This is a demonstration of reduced conflict cache miss with the higher set associative cache. If we think about how cache lines are loaded in different cache configurations, we see that, for example, block number 12 can go anywhere in fully associative cache, one of 2 places in two-way set associative cache, and only 1 place in direct mapped cache. Therefore, fully associative cache does not have any cache conflict miss, but has only cold and capacitor misses. Direct mapped cache has the highest conflict cache misses among 3 configurations. What about memory writes? Because the system can have multiple copies of the same data or instruction, we have to decide when to update other copies in the memory hierarchy. Write-through policy updates other copies immediately, and write-back policy defaults updates to low level until the cache line is replaced. By delaying updates, the hardware saves time, meaning better performance, but it has to keep track which copy is updated. Therefore, this policy requires additional control bit called dirty bit in each cache line. In other words, it's faster, but the hardware gets a bit more complicated. What about write miss? We have two choices. Write allocate policy loads a new cache line into cache and write. Write no allocate policy does not load cache line but updates the copy directly in low-level memory hierarchy. Typically selected combinations are write-through plus no write allocate or write-back plus write allocate. Because of locality, write-back plus write allocate outperforms, so almost all modern processors use this combination. Here's an example cache configuration of Intel Core i7 processor. It's a quad-core processor, so there are 4 identical cores. Each core has its own private L1 and L2 cache, and all cores share the last level L3 cache. L1 cache is a separate cache. It has a separate data and instruction L1 cache, not to destroy the locality each other. Its size is 64 kilobytes and use a 4-way, and its latency is 4 cycles. L2 cache size is 256 kilobytes and use of 8-way and 11 cycles. L3 is 8 megabytes and 16-way and 30 to 40 clock cycles of latency. The cache line size is 64 bytes for all caches.